schedule. So I did the best I could to get as much as I possibly could to you. It'll probably last us about a week and a half, 2 weeks, okay? We didn't get the full unit. I just couldn't manage getting it all done over the weekend because I had to do yours and BC's at the same time. So we kind of I split the difference and everybody got a part to get us for a couple weeks. So you'll have to pick up again in a couple weeks. But the good news is that I have most of the notes from BC that I did with BC for units 6, 7, and 8. So I just have to polish those up so that they're AB ready versus BC because they do a few things you guys don't do. So we will polish those and then hopefully we'll be able to pick up like one big note packet at one point and then not have to pick up for a while. Okay. All right. I think I hit record. We're ready to go. I'm going to start. Okay. I'm going to share my entire screen because I want to make sure we get through what I didn't record. Okay. So there is the essential question in the I-can statement. My goal, I believe, is to get you guys through example 2 live. Okay. And we will do, and then you're going to do example 3 on video. I don't know that I have that posted quite yet in Google Classroom. I just was working on it as you guys were coming in. The babies have been needy today, so I've been dealing with the babies. Did we enjoy the rain this weekend? Well, they're supposed to be writing the, that's not did I really post it? I posted in AB the BC stuff. That's good. Don't watch the BC stuff. I gotta get theirs posted in the right spot really quick. I am so sorry. Because they've got to do something for me before they come to class. This one. Create this one. Okay. Right. Ignore the posts in AB right now. Okay. We'll get rid of them. Okay. So, all right, let's get going, and then we will get you off to a break, and then working on the second half, and then I will, good morning, Hector, I will get you to, I will get some homework posted for you, okay? I think I made the assignment, I just have to get it posted. I believe it's a Delta Math assignment, okay? All right, so I turned on the noise canceling, so hopefully you don't have to hear. Toy Story 4 is the video of the morning in the background. All right. That one's kind of sad. It's not my favorite. Toy Story 2 all the way. That's the best one. All right, so we're going to use the mean value theorem today, and you're eventually going to be able to justify conclusions about functions by applying the mean value theorem over an interval. We've had another theorem, a big theorem called an existence theorem like this before, called the intermediate value theorem. And College Board loves to put these things on the free response questions, okay? So the homework I posted for today, good morning, Robert, is going to focus solely on the mean value theorem, though we're going to kind of see a little bit of mean and intermediate mingled. And then we're going to kind of do a lesson on, I think I have it scheduled for Friday, where we kind of see all of the theorems mixed together, okay? Again, you're going to see it a little bit today, but much more so. There's one more existence theorem we have to deal with on Wednesday, okay? All right, so, and you're going to feel like we amp up a little bit this week. I want to get 4 to 5 lessons in a week so that we are on track to make sure you have everything you need for May, okay? So, and also get review time in, all right? So we're going to pick up the pace. It's going to seem a little bit faster, but I want to make sure you guys have what you need. You're going to notice in here that there are places where I say extension, like in the last one. I'm going to put that extension work up this week, so that way you guys see, can start doing some extra. If you're intent on getting a 3, 4, 5, you might want to do the extension stuff, and it will count like extra credit. So if you're looking for extra credit, so see, I have extension. I don't have those ready to go yet, but they'll be ready in the next day, so you can do those. And then the stuff from Unit 4 that was extension, I'll have that ready and I'll be taking it through the end of the triad. Okay? So you guys have plenty of time to get that done still. All right, here we go. So we're going to talk about Rolle's theorem. It's kind of a little bit of an intro. It's a kind of a mini mean value theorem. So before we introduce the main topic of the section, mean value theorem, let's start with a special case of this important theorem called Rolle's theorem. So good old Rolle is over here to the side. Here's Rolle. Okay. I don't know why I have a white rectangle, but he came up with this theorem. It says place 2 points anywhere on the coordinate plane. So all I'm doing is literally following instructions. So I'm going to put a point here, and I'm going to put a, oh my goodness, it's not sticking. What's going on? Why is it not sticking? This is a problem if it doesn't stick, right? Let me just try closing and opening again. See if I can get it to reset. All right. Oh, it's stuck that time. There we go. I don't know why it wasn't sticking at the moment. All right, so 1 point. I'm going to put my other point right here. Okay. Then it says connected 2 points with a continuous function that is also differentiable. So remember, differentiable means no, I can't have corners, cusps, or I can't oscillate, and I can't have any vertical tangents. So it can't look like this anywhere where there's a vertical tangent. So as long as I don't have those things, we're differentiable. So I'm going to draw myself a nice little differentiable function. Okay, so there we go. Oh, wait, I didn't read the instruction. They're supposed to have the same y value, so I'm a little bit off on this one. They have to have the same y value, meaning they have to be up the same height. So let's try that again. So they have to be like this. And I'm going to do this. Okay, there we go. So conclusion, there must be at least 1 point in your function where you can draw a tangent line that is horizontal. Let's try that. Let's see if we can draw a tangent line that's horizontal anywhere. So I'm seeing one here. In fact, I got 3 horizontal tangent lines. So basically, this activity models the important concept called Rolle's theorem. So Rolle's theorem is that if we've got a continuous function and we've got a closed interval, and it's differentiable in the open interval, and you're to see that terminology a lot. So basically, they're usually going to say, hey, it's differentiable, and remember that implies that it's continuous. If our endpoints are equal, okay, so if our y values are equal, then there's going to be at least one time, remember derivative means slope, where the slope is equal to 0, okay? So in example 1, we have to determine if Rolle's theorem applies, okay? So I am looking for the word either continuous or differential, or I must have some kind of a polynomial function, okay? So it looks like I've got a polynomial, okay? We're on this interval -2 to 2. State thoroughly the reasons why or why not the theorem applies. If the theorem does apply, find the value of c guaranteed by the theorem. Confirm your result by graphing the function in the coordinate plane to the left. Okay, so first of all, I have to make a statement. Anytime I'm doing one of these existence theorems, I have to fulfill the if part of, so I have to fulfill the conditions, which are continuous and differentiable. I've got a polynomial function. We know all polynomial functions are continuous, and they're also differentiable. So I'm going to say that f, and I literally just have to make the statement that I verified that is continuous and differentiable. It's very rare that they're going to give you something that is not, okay? And you probably want to say -2 to 2. All right, so we can apply Rolle's theorem. So the next thing I need to do is I need to show that I have 2 y values based on these endpoints that are the same. So I'm going to plug in f of -2, and I'm going to plug in f of 2. And I know I haven't heard from them supposed to be today, so I'm going to plug in. So let's see if this works. Okay, so I want you guys to plug those values into here. I'm going to give you a minute to do that on your own. So everybody do that right now. Plug in the number -2 into this guy, and then plug in +2, and then I'm going to have you in a minute put your answers in the chat. Okay? I haven't heard from you yet. I want to make sure we're paying attention. Okay, so if your name starts, your first name starts with the letter A through J, you guys put in, so this is going to be A through J, you put in F of -2. And if your name starts with K through Z, put in positive. Tell me what it is the positive to. Tell me your answer in the chat. All I need is the number of your answer. Tell me the number of your answer. What'd you get? Hey, Mason is saying 8, Sasha. So we're looking like those. The second one looks like 8. Oh, Daisy says 8. I need some more people in the front part of the alpha here. I need my B's. Where are my B's? I had lots of B's in class. All right, so I'm pretty confident that this one is 8. I only have like one answer from the other one. Make sure you guys are participating because that's how you're telling me you are here. So I'm going to double check this one. -2 to the 4th would be 16. -2 squared would be 4 times -2 is -8. So I'm thinking that that one is 8. Thank you, Brianna. Is 8 as well. Watch it. You need to watch your sign though, okay, kiddo? Because I think it's +8. So what we have done here is we have verified that our y values are equal. So you want to make the statement there that therefore 3 dots means therefore f of -2 equals f of 2 equals 8. And Rolle's theorem applies. Okay. So what we get from Rolle's theorem is it tells us that the derivative is equal to 0. So I can take the derivative of that thing, set it equal to 0. We're going to find a c value, which is really just an x value. Okay. So f prime of x equals 4x cubed minus 4x. I'm going to set it equal to 0. In order to solve that, what are we going to have to do? So what am I going to have to do with this to solve it? Maybe something that starts with the letter F. What do you think? Tell me in the chat. What do you think? Jocelyn says that we are going to factor. Mrs. Ballard needs to plug in her machine. We are going to have a problem. All right, we are in fact going to factor. We're going to use a greatest common factor. So my greatest common factor is 4x. Hey, buddy, I need you to go watch a movie. You can't be in my lap right now. All right, and we're left with when I factor x squared minus 1 equals 0. I could factor some more, but I'm going to use a zero product property right here. So we have 4x equals 0, and then x squared minus 1 equals 0. So x equals 0, x squared equals 1. Take the square root, make sure you do plus or minus. We get plus or minus 1. We do need to verify that everything is on the interval, and our interval is from -2 to 2. So all of these values work. So all of those would be what they call the C value, which is really, again, just an X. All right, we are supposed to use our graphing calculator or something to verify that. So I'm just going to pull Desmos out really quick. So basically what we did is we showed what the zeros were, okay, based on Rolle's theorem. So we can, so just to prove to you that that actually worked, we're going to put that original function into Desmos. Here I go into Desmos. And I'm literally going to type in exactly what it looks like. F of x equals, and you can do this on your graphing calculator too. It just takes my calculator longer to turn on. Minus 2x squared. So there it is. And you'll notice, look, I have a 0, or I have a horizontal asymptote, right? That's what we were looking at. Horizontal asymptotes at -1, a horizontal asymptote at 0, and a horizontal asymptote, or it's not asymptote, a horizontal tangent, Mrs. Ballard, tangent at 1. So those are where my horizontals would be on my original. That's what we calculated. Or a slope would be equal to 0. So if you wanted to, you could sketch that guy over here. It went like this, to there, something like that. That's a terrible sketch, but close enough. Give me a couple of seconds to catch that up as we look at the next part, which I might not get to do without someone sitting in my lap. You want to sit on my lap? Can you be a good boy and not touch anything? Here, you need to watch the movie while you're sitting on my lap, okay? right, here we go. Let's look at this one here. So we're going to set the stage for what the mean value theorem is. Okay. All right. So when we see the words average rate of change, what algebra do we think of? Can you tell me that in the chat? What algebra do we think of? Average rate of change. Big hint, you can look at the little formula they've got there. What formula or what algebra do we think of? Big hint. It's the same thing we think of when we take the first derivative. Ah, there we go. There we go. It is the slope. Okay. It is the slope with the slope formula. And this is really what this is, right? That's the same thing as saying y sub 2 minus y sub 1 over x sub 2 minus x sub 1. It's just our x's and our y's are written a little bit fancy. This instantaneous rate of change is just the slope at a specific point, right? This is the slope over an interval. So that's the big difference. So interval slope means I need average rate of change. Slope at a single point means I want a tangent. Good morning, Kobe. And so I just want the slope at that one single instant. Okay, so the way that we do the calculations is slightly different. So the average rate of change, or what we call AROC, you may not use that abbreviation on the calculus test, would be, in this case, it says we're going to find it from 1 to 5. Oh, and they gave us a function up here at the top, so we're going to use this function up here. So what I would do is I would calculate f of 5 minus f of 1 over 5 minus 1. All right, if I put 5 into here, that will give me 5 squared minus 20 plus 5. So that would be 25 minus 20 plus 5. So 30 minus 20, which is 10, right? And then when I put 1 in, I would get 1 squared is 1, 1 times 4, negative 4 is negative 4 plus 5. So that looks like it would give me 2 all over 4. So I would get 8 over 4 or 2 for the average rate of change of that problem. Now, for instantaneous rate of change, I have to have an x value at a point. They didn't give me that, but I could take my first derivative and at least get the instantaneous rate of change for the function, which would, what is the derivative of this? I haven't asked a question in a minute or two. What's the derivative of this function up here? You guys tell me in the chat. Let's see if we still remember how to do that part. What's the derivative? It's good when we have a nice, easy derivative, right? No product rule, no chain rule, no quotient rule, right? It's nice when we have an easy one. So we're going to have 2x minus 4. But unless they give me an x value, I can't find it at a point, right? They have to give me an x value to find the instantaneous rate of change. All right, so then they're asking me, is there a value where the instantaneous rate of change equals the average rate of change? So let's set this up like this is a word point, right? It says instantaneous equals average rate of change. So I'm literally going to take my instantaneous and I'm going to set it equal to what we got on our average rate of change and see if I can find an x value where they're equal. Okay, so let's see. I've got 2x equals what? 6, x equals 3. So it's saying that the slope at x equals 3 is equal to the slope of the average rate of change. Well, let's go ahead and look at that on the graph. You'll notice that at x equals 3, my tangent line slope matches the slope of when I connect the 2 points. Okay, so basically what we just did is we just did a proof of the mean value theorem. So there's always going to be a point when I connect any 2 points on the function, as long as I'm continuous, as long as I'm differentiable, where my instantaneous rate of change's slope equals the average rate of change's slope. Okay, so we kind of proved it right there. So I'm going to just read through the paragraph. In the example above, we were able to find a value in the given interval where the AROC equals the IROC. It is natural to wonder if this is always the case. can we always find a place where f prime equals the average rate of change in the given interval? And the answer is absolutely yes, as long as it is continuous, and I know I'm adding this in, and differentiable. If it's not those two things, we won't be able to do it. So this is the basis for the mean value theorem. So the mean value theorem is something that we call an existence theorem. And an existence theorem basically says that, hey, this thing exists whether or not we can prove it with actual numbers. We know it's to be true. Okay. Intermediate value theorem was another existence theorem, and on Wednesday we're going to learn a third one called the extreme value theorem, which we did play with. We kind of played with last year, you just didn't realize it. So this type of theorem is important in mathematics as they guarantee that a value exists. Catch up here. Okay, let's keep going. So for each of the functions below, draw the segment between the indicated points on the graph. Is there a point on the graph between the indicated points where the slope of the line tangent to the point is equal to the slope between the 2 points? If so, sketch the tangent line. So this isn't the entire problem. When you go to do your homework on Delta Math, it does have you sketch this, okay? But then it has you go a little bit further. The further part is what we're going to do in example 3. Okay. So first thing it says is, hey, sketch a point between the given point, or sketch a line between the given points. So I see a point here and a point here. I'm going to sketch a line between them. If I could pull out a ruler and try to sketch something that was parallel, I would try to do that. I can't quite do that. I could kind of look at the slope. It kind of looks like up 1/1. So I'm thinking it's looking, I could probably get a tangent line down here, kind of do an up 1/1 kind of thing. But probably about right there. It doesn't have to be perfect. And it might at some point go through the function somewhere else, but it's tangent at that value right there. Okay. So on this one, yeah, we were able to do it. That one's a definite yes, that the mean value theorem works. Okay. All right. So earlier in the lesson, we'll see who was paying attention now. Okay. Earlier in the lesson, we said it had to be continuous and differentiable. Okay. So remember that continuous means I can't move my pencil. To draw the function of the picture I have to be, wouldn't pick up my pencil, so there's no holes. Differentiable means it has to have no corners, no cusps, no vertical tangents, and it has to be oscillating. So is this function here continuous? So is it continuous? Yes or no? Tell me in the chat. Is it continuous? Okay, so we've got a little bit of difference of opinion. So I'm going to show you how the continuity of it. So as long as I can draw it without picking up my pencil, it's continuous. So it's yes, continuous. So it fits that part. Is it differentiable? Meaning it has a smooth curve. There's no corners, no cusps, no vertical tangents, no oscillating. Is it? It's not differentiable, right? Because we've got all these corners. Not differentiable. Okay. So in this case, there are no points tangent. So this one would be a no points tangent. We could still connect these values, right? I could still, the wrong color. I could still connect them, but there aren't going to be any places on there that I think get tangent because it's not a differentiable function on the entire interval. Okay. All right, let's take a look at, and I apologize if something goes haywire because I have little fingers helping me out now. Huh? Don't touch. Okay. All right. Oh, you're going to be crabby, huh? All right. Do you like that face? That was a good one, wasn't it? All right, so let's look at this one. Let's see if we can connect. So first of all, is h of x here? Is that one continuous? So is it continuous? All right, awesome. I'm definitely getting continuous on that. Is it differentiable? As in there's no corners, no cusps, no oscillating, no. Yeah, good job, good job. So MVT should apply, right? So let's see if we can draw it on there. So I know I'm going to connect these 2 points with a secant line, but then I need to draw a parallel line somewhere on here that looks approximately tangent. I'm kind of thinking it's like right in there. This we're just practicing, so it doesn't have to be perfect. I don't know what the tolerance is going to be on delta mass, so you might have to play with it a little bit. Okay. All right, looking at the K of X graph. Is the K of X graph continuous? No, it's not. Good job, you guys. This is a really good review of our unit 1 definitions, right? So it's not continuous. No, not continuous. I'm not spelling continuous even close to right. I am sorry about that. So I could still connect my points, right? But there's nowhere, because of the continuity break, there's nowhere where I can officially make the theorem make a tangent line. Okay, please don't do that. All right. So in the examples above, which graphs were we able to find a point between the indicated points where the I rock equals A rock? Okay. No, it's not your turn to pick yet. This movie's not over yet. Okay. Okay. He wants to watch this lovely little dino program. It's not exciting at all. All right. So we actually answered the questions as we were going through it because I kind of talked through it. So which graphs we were able to actually find us working on was f of x and h of x. So f of x and h of x, and the things that they had in common were that they were continuous and differentiable on entire interval. Okay, I'm going to give you a second to write that. Okay. So here's what the plan is for the rest of this. Okay. I don't have it up there yet, but I'm going to have it up there in the next 5 to 10 minutes, and I will text you when it's there. Okay. You're going to finish the lesson because I did the rest of the lesson on video because I didn't know how long the first part would take us. It didn't take us as long as I thought it was going to. Given that I have a cranky 2-year-old on my lap, I'm going to let you watch the rest on video. Okay. So you're going to go through that. You're going to hit a spot where it says extension. I don't have those videos yet because I was filming while I had cranky kids. So I will film when my husband gets home and the kids aren't cranky. I'll have all the extension, the Unit 4 and this extension up by this evening for you. Okay. So you can start working on extension work if you wish. The extension is totally optional. You don't have to do it. It's optional. Okay. So I won't specifically on our unit test on extension stuff. Okay. All right. And then I will also, you'll get to pick in a little bit. Okay. All right. We've got to do a joke of the day because I think we need one. Andy filmed me a new one here. And then after you're done with this assignment, there's going to be a Delta Math assignment. It's already in Delta Math. I just haven't put the link in Google Classroom yet. Okay. All right. So let's do the joke of the day because it's Monday and we need it. Is anyone wearing flannel?